long distances by generating and sending an electrical signal called a nerve impulse, or action potential. Your goals for learning are to understand that rapid changes in permeability of the neuronal membrane produce the action potential, to recognize that altering voltage-gated ion channels changes membrane permeability, to understand the movement of sodium and potassium ions during the action potential, to examine refractory periods, to learn about conduction velocity. Here's what you need to know: the location and function of voltage-gated channels, how electric signals are measured inside cells, the difference between positive and negative feedback loops, how axons are insulated with myelin. To see definitions of terms, click the bold red words. To review the process of myelination, click the link button. If you use a link button, you can return to the page you started from by clicking the return button. The action potential is a large change in membrane potential from a resting value of about minus 70 millivolts to a peak of about plus 30 millivolts and back to minus 70 millivolts again. The action potential results from a rapid change in the permeability of the neuronal membrane to sodium and potassium. The permeability changes as voltage-gated ion channels open and close. In the following pages, we will study, step by step, the changes that occur as an action potential is generated and then propagated down the axon. The action potential is generated at the axon hillock, where the density of voltage-gated sodium channels is greatest. The action potential begins when signals from the dendrites and cell body reach the axon hillock and cause the membrane potential there to become more positive, a process called depolarization. These local signals travel for only a short distance and are very different from action potentials. We will study them in a separate module that covers synapses. Click the neuron to see the axon hillock depolarize. As the axon hillock depolarizes, voltage-gated channels for sodium open rapidly, increasing membrane permeability to sodium. Sodium moves down its electrochemical gradient into the cell. Click the membrane to depolarize the neuron. Watch the sodium ions. If you'd like to see the animation again, click the membrane. If you'd like to see the animation again, click the membrane. If the stimulus to the axon hillock is great enough, the neuron depolarizes by about 15 millivolts and reaches a trigger point called threshold. At threshold, an action potential is generated. Weak stimuli that do not reach threshold do not produce an action potential. Thus, we say that the action potential is an all or none event. Action potentials always have the same amplitude and the same duration. Click the neuron to depolarize it. Watch the graph of the membrane potential as the neuron depolarizes. Will there be an action potential? That's right. This depolarization has not reached threshold. Click the neuron again to depolarize further. Will there be an action potential? That's right. This depolarization has not reached threshold. Click the neuron again to depolarize further. Will there be an action potential? That's right. At minus 55 millivolts, the membrane is depolarized to threshold and an action potential is generated. Threshold for this neuron is minus 55 millivolts. Threshold is a special membrane potential where the process of depolarization becomes regenerative, that is, where a positive feedback loop is established. We will study the positive feedback loop on the next page. When and only when a neuron reaches threshold, a positive feedback loop is established. Click the neuron to depolarize it to threshold. At threshold, depolarization opens more voltage-gated sodium channels. At threshold, depolarization opens more voltage-gated sodium channels. The rising phase of the action potential ends when the positive feedback loop is interrupted. Two processes break the loop: the inactivation of the voltage-gated sodium channels, the opening of the voltage-gated potassium channels. We'll look at potassium channels on the next page. To see what happens to the sodium channels, click the neuron. The voltage-gated sodium channels have two gates. A voltage-sensitive gate opens as the cell is depolarized. A second, time-sensitive inactivation gate stops the movement of sodium through the channel after the channel has been open for a fixed time. We'll observe the events at the voltage-gated sodium channels all at once. Then we'll see them step by step at a single channel, and then we'll put them all together again. Click the membrane to depolarize the neuron to threshold and start the animation. To observe the events at a voltage-gated sodium channel step by step, click the designated channel. At the resting membrane potential, the voltage-sensitive gate is closed. Click the channel again. As the neuron is depolarized, the voltage-sensitive gate opens. Click the channel again. At a fixed time after the channel opens, it inactivates. Click the channel to repeat the animation, or click the membrane to continue. Let's watch the sodium channels again. At the peak of the action potential, voltage-gated sodium channels begin to inactivate. As they inactivate, the inward flow of sodium decreases and the positive feedback loop is interrupted. To see the animation again, click the membrane. We've looked at the sodium channels. Now let's see what happens to the potassium channels. The voltage-gated potassium channels respond slowly to depolarization. They begin to open only about the time that the action potential reaches its peak. Click the membrane to depolarize the neuron and initiate an action potential. You've seen that potassium moves out of the cell as voltage-gated potassium channels open. As potassium moves out, depolarization ends and the positive feedback loop is broken. Click the membrane to repeat the animation and observe the interruption of the positive feedback loop. You have seen potassium leaving the cell as voltage-gated potassium channels opened. With less sodium moving into the cell and more potassium moving out, the membrane potential becomes more negative, moving towards its resting value. This process is called repolarization. Click the membrane to see the animation and graph of the action potential. In many neurons, the slow voltage-gated potassium channels remain open after the cell has repolarized. Potassium continues to move out of the cell, causing the membrane potential to become more negative than the resting membrane potential. This process is called hyperpolarization. Click the membrane to see the rest of the action potential. Watch the graph. By the end of the hyperpolarization, all the potassium channels are closed. As you have just learned, the opening and closing of voltage-gated channels changes the cell's permeability to sodium and potassium during the action potential. Now let's watch this happen. Begin by clicking the portion of the action potential graph where the sodium permeability is increasing rapidly. Yes, sodium permeability increases rapidly during the rising phase of the action potential. Now click the portion of the action potential where sodium permeability is decreasing rapidly. Yes, sodium permeability decreases rapidly during repolarization. We can graphically illustrate what you have just seen by superimposing a graph of sodium permeability on top of our graph of the action potential. Click the action potential graph to see the sodium permeability graph shown in red. Now click the portion of the action potential where potassium permeability is greatest. Yes, potassium permeability is greatest. We can graphically illustrate what you have just seen by superimposing a graph of potassium permeability on top of our graph of the action potential. Click the action potential graph to see the potassium permeability graph shown in blue. Now let's see the simultaneous changes in sodium and potassium permeability during the action potential. Click the graph of the action potential. The rapid increase in sodium permeability is responsible for the rising phase of the action potential. The rapid decrease in sodium permeability and the simultaneous increase in potassium permeability is responsible for the repolarization of the cell. The slow decline in potassium permeability is responsible for the hyperpolarization. To repeat the last animation, click the graph. During an action potential, voltage-gated sodium channels first open rapidly, then inactivate, then reset to the closed state. Voltage-gated potassium channels open and close more slowly. Click each phase of the action potential to see the state of the voltage-gated sodium and potassium channels. Voltage-gated sodium and potassium channels are closed when the neuron is at rest. Voltage-gated sodium channels open rapidly, resulting in movement of sodium into the cell. This causes depolarization. Voltage-gated sodium channels begin to inactivate, and voltage-gated potassium channels begin to open. This initiates repolarization. Voltage-gated sodium channels continue to inactivate, then reset to the closed state. Potassium channels continue to open. This results in a net movement of positive charge out of the cell, repolarizing the cell. Some voltage-gated potassium channels remain open, resulting in movement of potassium out of the cell. This hyperpolarizes the cell. Just after the neuron has generated an action potential, it cannot generate another one. Many sodium channels are inactive and will not open, no matter what voltage is applied to the membrane. Most potassium channels are open. This period is called the absolute refractory period. Click a channel and then a button to predict the state of each voltage-gated channel at about the midpoint of the absolute refractory period. Immediately after an action potential is generated at the axon hillock, it is propagated down the axon. Positive charge flows along the axon, depolarizing adjacent areas of membrane, which reach threshold and generate an action potential. The action potential thus moves along the axon as a wave of depolarization traveling away from the cell body. Click the axon hillock to see an action potential generated and propagated along the axon. Conduction velocity is the speed with which an action potential is propagated. Conduction velocity depends on two things: the diameter of the axon and how well the axon is insulated with myelin. Let's look first at axon diameter. Click an axon to see how diameter affects conduction velocity. As the axon diameter increases, the internal resistance to the flow of charge decreases and the action potential travels faster. Now let's see what happens to the speed of the action potential when the axon is insulated with myelin. The diameter of the axon now includes the myelin sheath. Recall that myelinated axons have areas of insulation interrupted by areas of bare axon called nodes of Rambier. In a myelinated axon, charge flows across the membrane only at the nodes, so an action potential is generated only at the nodes. The action potential appears to jump along the axon. This type of propagation is called saltatory conduction. Predict which axon will have the fastest conduction velocity by clicking that axon. Correct. More speed is gained by insulating an axon with myelin than by increasing the axon diameter. Here's a summary of what we've covered. The action potential is an all or none event that can travel for long distances because it is a regenerative electrical signal. When the axon hillock is depolarized to threshold, an action potential is generated. Voltage-gated channels open, thereby increasing permeability of the neuron, first to sodium and then to potassium. As sodium moves rapidly into the neuron, it produces the rising phase of the action potential. As the inward movement of sodium slows and the outward movement of potassium increases, the membrane repolarizes. Immediately after an action potential, the neuron cannot generate another action potential during the absolute refractory period. During the relative refractory period, it can generate another action potential only if stronger stimuli arrive at the axon hillock. The diameter and myelination of an axon determine its conduction velocity.